So, do you have signal now? Okay. Started here. So my name is John Walrand, and you can always get in touch with me at john.walrand@colostate.edu. This next list is the GTAs for the course. Now, only a fraction of you are actually in here in person, which frankly is a little odd after a year and a half, but here we are. And there are all these GTAs, both for you and for the two other sections, one of which are CSU students who are online, and another group that are not CSU students are online. And that's really the vast majority of the class. So we're going to have a lot of TAs. The TAs will be Michelle Staros, Davis Rana Guerrera, Madison Prop, Abby Jefferson, Ethan McNally, Katie Brown, and Saspa Hotness. That's the list of GTAs. Use them. They are really, really helpful references to you. And they'll be having office hours, and they'll be having discussion groups. Go to them. They are there to help you out for this course. And before we get too far into it, I should say that I think over the years I've discovered that this course is not the same as a lot of other courses. It's not a memorization course. It's much more a concept course. And I'll be giving you stories and presentations. And those stories and presentations, I'll expect you to learn and then apply them to novel problems. I think that's a little bit different than most courses. This is not a course where I'll give you a series of slides and then give you a series of bullet points and expect you to repeat that on the exam. That's not what we're doing in here. So it's a different approach, and it requires you to become familiar and fluent with all of the stories they tell. Physiology is one of these disciplines where it's very conducive to stories, very conducive to concepts. And so if you can get the stories and the concepts down, this is not a difficult course. But if you try to memorize every fact that comes at you, it's going to be overwhelming because we cover a lot of information. So one of the challenges here is to aggregate the information into pieces that are bite-sized and then string them together to tell the story. And you are responsible for doing that. Now, you're not entirely responsible on your own because, after all, you have all the help from all of these TAs, and so use them. They're there for your help. Now, what I'm going to do now is I'm going to turn the floor over to Abby Jefferson because she's going to go over the materials on the front board and walk you through some of the way the points are going to be distributed. We're trying a new experiment this summer on how to give the extra credit points and keep them somewhat similar. I'm sorry, keep them separate from the exam grades. So we're going to put them in a different Canvas course, and she'll explain that all to you. So I'll turn it over to Abby.
So I just really briefly want to say, in the same kind of vein, I know a lot of students are taking this class again. Oh, do I need a microphone? I need a microphone.
Yes, you need a microphone. So now.
1 second. Okay, can you hear me? Okay, wonderful. So I just want to reiterate what Dr. Warren is saying. This is a challenging course for a lot of people, and I know a lot of people here maybe, and certainly who are listening at home, will be taking this course again. I want to be really clear that a lot of folks think that if you've just seen the material once or twice before, maybe this time it'll sink in. It's not true with this course. I mean, maybe for some of you some of the time, but generally it's not true. If you just try harder in this course, that might help. That might be part of the problem, but generally that's not the only thing that's going wrong with your studying. And I'm looking at a very small group of people here. I'm not staring at you, I swear. I'm also talking to all of you people at home too. So please, if you're taking this course again, for whatever reason, maybe you had a disaster last semester, whatever it is, please, please, please come and talk to us. We have a horde of GTAs, and we're all really excited about teaching, and we're all really enthused to help you. We have lots and lots of techniques that you can use to improve your study methods that we've actually, we've tested them on students, we've got them from scientific literature, and then we've tested them year after year with other students, and we've seen that they can be successful. I believe every one of you can be successful in this course. But you might need the right tools, and we have those. Okay, So that aside, I'm going to add our email up here in a second when I stop talking. And you can email us that way. And I guess I'm going to briefly go through our extra credits. So we have our selection of extra credit here. Here's the key point. Everything that is extra credit is available through a separate Canvas course. So if you haven't got an invite to that and accepted it yet, either accept it or send us an email if you haven't got the invite, so that you have access to all of this. The other thing is that this is half a letter grade. That's a lot of extra credit. We're not going to add more pretty much ever as the semester goes on, so these are the options that you have now. The first one is lecture quizzes. So each class we're going to have, is it 2 lecture quizzes? I think it's 2 lecture quizzes because we're doing 2 lectures a day in the summer. They're going to equal a total of 5 points over the semester. They're going to just be a couple of questions that we think highlight some of the key ideas from class. And of course, we're going to have the occasional practice exam question in there too. Now, don't expect the exams to look exactly like these except for the practice exam questions. He has an amazing way of writing exam questions that is quite challenging. This is just to get you comfortable with the material, but we can work on getting you comfortable with his style of exam questions in other sessions. We also have tutorials where UTAs are going to be, so that's undergraduate teaching assistants, are going to be hosting kind of a lesson based on whatever we're going through at that particular point in time. They will have practice exam questions too. They tend to be very helpful. These folks have done very well in this class in the past, are very comfortable with the material, and are happy to help you out. So you can get 5 points from that too. I think the way this is set up is that you have 2 tutorials that you can go to a week. That kind of maxes out the possible points you can get, but you can go to as many tutorials as you want. Let's see. Then we have worksheets, and we've actually pulled this from a class that we actually charge for in the spring and the fall. These are recitation worksheets, and this is to help you kind of dive into the material a little bit more and get more comfortable with it. We're going to post a video kind of addressing the things that you really need to know in order to do this video once a week, or in order to do this worksheet once a week. And then we're going to have a live session each week too, where you can come and ask us questions about that. So you'll be graded on successfully doing the worksheet, but we'll have lots of opportunities to get full points on that. Yes, okay. So then finally, there are ebook quizzes. And Dr. Warren has written an amazing ebook that is a very good reservoir of information. It does push you a little bit ahead of where we're going to be in class. And each week, we're going to have is it each week, or are we doing 2 per week? 2 per week. We're going to be having 2 quizzes per week that will push you ahead in that material and hopefully make it so that when you sit down in class, you're ready to learn the details that he's going to give you. Does that make sense to everyone? Yeah, question in the back.
Can we retake the lecture quizzes or the ebook quizzes? Just like one take and you're done.
You cannot retake the ebook quizzes. I don't think, I'm going to have to double check, and I'll answer in the live chat. I'm going to double check on the lecture quizzes. I think there's 1 for credit, but I think there's no harm in taking it again. I think you get to see it afterwards. But I'll double check on that and get back to you.
Thank you.
Any other questions? Concerns, comments? Have I drilled the idea that you need to come talk to us if you're taking this class again, or if you're just nervous about this class? Yes, I'm getting nods. I love this. I get interaction. I get real students. Yay. Okay. Last thing. Those of you that are in here, so this doesn't apply to the folks listening at home, but for those of you that are in here, when you sat down, you should have sat down with a sticky note. That sticky note, you'll have to enter that information on Canvas. So this up here is your seat number, and this down here is the code. This makes sure that you get a seat every single day in class, and it'll be the same seat all through the semester. Did I miss anything?
I don't think so.
Lecture quizzes are 1 attempt.
Thank you, Madison. Okay, so come talk to us.
You only have 1 attempt on those quizzes, but they'll be open after that, so you can see the answers. It's not as though we're going to close them up to you and you'll never see them again. So bear with me a moment here. So we have signal up there? Okay. Okay, to get started again. So this is a really important email address. Most of your interaction with the TAs will be through this email address. And it's just a common place where all of you can go and get information. Now, the way I normally set up my lectures is that I put these outlines in the board. And it gives you a reference of what we're going to talk about during the day. Also, it gives me a reference when I'm in the room lecturing, so I can go back to it and see where we actually are. But it's an advantage to at least those of you who are in this room, because you can see something on the board that I'm talking about and come back here to see where it is in the outline. And typically in my lectures, what I'll do is I'll go through this outline to tell you the main ideas that we're going to cover in that day. And don't underestimate the importance of these. When I sit down and write an exam and I look back over the exams I've written, for the most part, the questions that I have on the exams are drawn from these introductions. So this is a summary, and if you're fluent with this summary, you're in pretty good shape for the material. But you do have to become fluent with the material and be able to talk about it off the top of your head. In some cases, if you can't get together with other people to study, and that's been a real difficulty for the last year and a half, I think talking to other people, conversing with other people was a real advantage before the pandemic, and now we're breaking out of this. So if you get a chance to be with other people and discuss with other people online or in person, please do it. I think it'll be a big help. So what I'll do first is we'll walk our way through the syllabus. Most of you have probably read it. We'll walk our way through it, and I'll spend a few minutes on that. And then we're going to spend some time on real information. And we're going to start with the discussion of water. And many biology courses start with this because all of life takes place in an aqueous environment. If you've been following the information about Perseverance and the Mars explorers, they're looking for creatures that may have once existed on Mars in an aqueous environment. It was one of the great breakthroughs when they found that there was once a water environment on Mars. And we're thinking if life is going to occur as we know it on this planet, it's going to occur in a water environment. And so that brings us to this idea of what's unique about water. So I want to spend a little bit of time talking about the unique characteristics of water which allow biology to flourish where we live. And we'll see that it's a simple molecule. It has a molecular weight of 18. It's composed of a single molecule of oxygen and 2 atoms of hydrogen. And so that gives us a molecular weight of 18. And we'll compare that to 2 other similar small molecules, oxygen and nitrogen. Oxygen and nitrogen make up the atmosphere around us. About 79% of the atmosphere around us is nitrogen, about 21% is oxygen, and yet it's a gas. And in fact, we'll walk our way through some of the characteristics and try to sort out why water is so much different than these other molecules, even though it has a lower molecular weight. We're going to see that the crux of that argument is that something called the dipole moment. The dipole moment is peculiar to water because of the unequal sharing of electrons in the water molecule, and we'll talk about that. This unequal sharing of electrons in the water molecule gives rise to a number of properties, some of which we're used to every day. These are the properties which allow water to be liquid at room temperature between 0 degrees centigrade and 100 degrees centigrade. It's the characteristic which allows ions to go into solution in water. It's the charge on the molecule. And then finally, there's this concept of hydrophilic, which before we get to that, we'll talk about surface tension. It's the dipole moment generating a surface tension. This is something that's of interest in terms of water, and this will become important when we begin talking about the respiratory system later in the semester. And the third idea here is the concept of hydrophilic, water-loving, why things will go into solution. That then will bring us to this idea of diffusion and equilibrium, it's really difficult to overemphasize the importance of diffusion and equilibrium in this course, because all of biology depends upon this idea of the random walk of molecules. It doesn't matter whether we're talking about the movement of ions across membranes in muscles and in nerves, or whether we're talking about the movement of carbon dioxide and water across the respiratory membrane in the lung. It's all a random walk. It's all diffusion. It's all about coming to equilibrium. And so we're going to spend a little bit of time here talking about how if we put a molecule such as sodium chloride with its two ions, one sodium, one chloride, in water, and that then goes into solution in water, what happens to those ions? We're going to spend some time talking about that. That's going to bring us to the idea of hydrophilic. And we're then going to see how those ions will diffuse through the water column, become randomly distributed in the water column. So we'll talk about diffusion in the water column, then we'll follow that with diffusion across a barrier. It's important to think about diffusion across a barrier because when we talk about the movement of ions into and out of cells, they're going to be moving across the barrier of the biological membrane. And so we have to think in terms of how ions will move from a region of higher concentration to a region of lower concentration. It's just thermodynamics. It's just the idea things go from higher to lower concentration, but it's an important concept in all of biology. So we'll spend a little bit of time on that. And then we'll switch gears, but it's the same concept. That is the diffusion of water. Diffusion of water has a special name. It's called osmosis, and it occurs through special channels called aquaporins, and we'll spend some time talking about that. And then we'll go to the other extreme on the spectrum. We'll go from hydrophilic to hydrophobic. Hydrophobic comes from the Greek. It means water-fearing, and the characteristics of molecules that are hydrophobic is that they typically have their electrons equally shared. Because they're equally shared, they're not polar, they're not charged, and they don't easily go into solution in water. And we'll talk a little bit about that in terms of triglycerides. Triglycerides are fats. This is an idea that will occur over and over again in the course. And triglycerides, because of the way they're organized, based on a 3-carbon structure of glycerol connected to ester bonds to a fatty acid created by dehydration synthesis, these gigantic molecules will now have almost no charge. Because they have almost no charge, they're hydrophobic, they don't easily go into solution in water. So we'll have these two extremes, hydrophilic and hydrophobic. And then we'll bring these ideas together and we'll think in terms of something called amphipathic. Amphipathic again comes out of the Greek. It means both feeling. And an example of an amphipathic molecule is a phospholipid. We'll talk about phospholipids. They are basically a kind of triglyceride, but there's a subtle difference. Instead of having 3 fatty acid side chains, they only have 2. The third fatty acid side chain is now replaced by a phosphate head group, which is charged. That charge on the phosphate head group now gives it a hydrophilic characteristic, and now this is a molecule that can live in both a hydrophilic and hydrophobic environment. And because of that, we're going to see that we're going to use these amphipathic molecules to make the phospholipids, and the phospholipids are now going to make a lipid mosaic model of the membrane. We'll finish the story today with the lipid mosaic model of the membrane, which is a phospholipid bilayer, which is then punctuated by transmembrane proteins. But before we get into the nuts and bolts of that, let's spend a moment on talking about the syllabus. The course objectives are to give you a broad background in physiology. There are some prerequisites here. You should have a background of a semester of college biology and a semester of college chemistry. You can get through this course without them, but we just find historically that students who have had that background find this course way easier than those who haven't. Some of it's language. Some of it is, if you've had the biology, the language would be more familiar to it. And if you've had the chemistry, we're not going to do a whole lot of chemistry in here other than naming molecules. We're not going to be balancing equations or any of that sort of thing. But there's some terminology in the chemistry that you'll need to know. You basically need to be fluent with the idea of moles and millimoles. You need to be fluent with the idea of ions. And so the background in chemistry is important, but it's not essential. So if you haven't had it, beware, but you can be all right, particularly if you use the help of all of the TAs. So we know that we've taken you through the online stickers, and if you're in the in-person course, soon in the next week or so, you should take the Respondus quiz, because if you are in the online course, you need to take the Respondus quiz, because all of your exams online will be through Respondus. For those of you in here, don't worry about that. You'll all have paper exams in here. There is an optional textbook if you like to have a hard copy textbook. I'm not sure how many people deal with these anymore, but if you have a hard copy textbook, if you like to have a reference text, I'd go get the Vander's Physiology. The reason it might be useful to you is that it has an index. I wouldn't read it like a novel. There's way, way too much information in it. And so, it's sometimes useful to go to a concept of something we've talked about in class, look it up in the index, and then look at the few paragraphs from the index about that particular topic. It'll give you an advantage, too, of looking at another series of figures beyond what I show in class and draw on the board. So that's the main advantage, but don't buy it new. I would go to one of the online booksellers and get a used copy. They reissue these editions every couple of years, and there's nothing in here that you need the most recent edition for. It's just going to be a reference text for you. The ebook is required because it basically has all the objectives for the course, it has all of the main ideas in the course, and all of the ebook quizzes. Now, Abby mentioned the ebook quizzes, and it's unusual for most of you to take a quiz on something you haven't talked about before. But what we're trying to do with those ebook quizzes is we're trying to give you some familiarity with the material by reading the narratives associated with figures, and then answer questions about that narrative. And those questions will not be on the material we've already covered. They'll be on the material we'll cover in a few days or a week or so. And the reason for that is I think that if you run through that material, look at those figures, you'll have much better familiarity with the material as we cover it in class. And the advantage of that is you are familiar with the language. There's a lot of new language in here. And I've talked to students who say that one of their problems was they would hear a word. It was a new word, and then they were concentrating on what the word was while the lecture was continuing on. And so I think the more familiarity you can have with the language before you get here, the better off you'll be. So again, for expectations, we expect you to become familiar with this material and fluent with it. Teach someone else. If you have to, teach your cat. But there's something about verbalizing this material and telling the stories that I think is really important. There will be a lecture video, and so all of you in the in-person class can watch that lecture video later. What we're doing right now is we're live streaming this lecture out to the people who are in the online sections, so they can watch it live as well. And it's accompanied by a chat box, and Abby or Madison will be answering questions in that chat box as we go along. That chat box will be available to you later on. It takes about 24 hours before that comes out, but you'll be able to look at that. I think there's a real advantage to coming to class. I think there's a real advantage to sitting in a classroom. I think the number of advantages are, first, you've been trained since you were 5 years old to be in class at a particular time and spend time in class for that period and concentrate on the material in front of you. If you're in the online class, I really encourage you to attend class as the live stream. If you possibly can, I think it's a good idea, partly because it sets a regimen. One of the real problems in this class, particularly for students online, which we've discovered in the last year and a half, is there's a real propensity to put off studying, put off watching the lectures. So, I'll get to it on Sunday. And then you have 10 lectures to watch on Sunday. Well, that's a hopeless task. And one thing leads into another, and you really need to consolidate this material every day. Rule of thumb. This is 100 minutes worth of lecture, and the rule of thumb says you should spend twice that amount of time out of class as you spend in class. That brings you to close to 5 hours a day for this course. That's a big number, but it's just the way it is. It's double. It's a 16-week course taught in 8 weeks, so we really have no choice but to give this material to you, and then you have to focus on it. Don't get behind. That's the real pitfall in this course, whether you're online or on campus. Putting things off and not getting to them till later is a real problem because you need to spend time with the material, learning the material, and becoming fluent with it. So Abby's taken you through all of the extra credit points, and this will be a little different. We're sort of doing an experiment this summer to see if we can make that work. And there are a number of tutorials that will be offered. You should go to those. I think they're very helpful. They're undergraduate students who've done a good job in this course. They like to teach, and they'll spend time with you. So there's meant to be small group discussions, again, where you can verbalize things. I'll let you go through the academic integrity piece. Exams. There will be 4 unit exams and a final. And there'll be a total of 500 points in the course, but the final will count twice. So this is the way we run the course. There are 4 unit exams, each worth 100 points. The final is worth 200 points, so that's 600 points. Well, where does the 500 come from? Well, the way it's set up, and for most people, what we'll do is we'll drop your lowest score on the unit exam and count the final twice. So you'll have 3 unit exam scores and your final will count twice. Because we're dropping the low score, though, if the low score is on the final, we'll drop the final score and count your 4 unit exam scores, and the final exam will only count once. There's a table in here explaining all that. But fundamentally, it puts a lot of weight on the final. It is a comprehensive final. And I try to ask questions on the final that are drawing ideas together so that the unit exam questions are not the same on the final as you saw in the unit exam. They'll be drawn together, trying to stitch together the major concepts. If I'm doing it right, the questions on the final are much more conceptually oriented. Each exam will be worth 100 points. There will be 20 points of those as fill in the blank, and 80 points will be multiple choice questions. You'll have 2 hours to take the exam. We'll start in here at 9, it'll go to 11, and it's true for the online students. They'll start at 9 and go to 11, but they have a broader window in which to take it. The students in the 401 section can take the exam anytime between 9 and midnight, and the students in the 801 section, because it's a true online course, and a lot of students are trying to work and do other things, that exam window will be open for the following day as well. If you have special needs and you're dealing with students for the Disability Center, let us know. We've worked with them for years and we have a good working relationship with them. If you've got extra time in exams, let us know. We'll send you off to the exam center to take those exams so you'll have extra time. And if you're online, let us know. We'll add extra time to those exams in Canvas. If you're auditing the course, let me know. There's special rules about that. If you're completing an incomplete or you're retaking the course, again, let me know. And I will give you instructions on how to get a new access code from the ebook publisher. It's just web support at greatriverlearning.com, and explain to them that you're retaking the course. They'll check their records and send you a new access code, so you don't have to buy the access code again. The rest of it is just the schedule of lectures. That's a suggestion. Probably won't be absolutely on that schedule, but it's fairly close. And it gives you some idea of what's going to be covered every day. Most of the lectures are going to be given by me, but the last week, Dr. Bauma will come in and he'll give the lectures on reproduction. I know nothing of reproduction. I don't know how I had children. And so I don't lecture on that material, but everything else I'll be telling you about. So any questions on that? And another point here too, it's really nice to be in front of a class of students again. It's nice to be able to talk to people and get some feedback. So if you want to ask questions, please feel free to ask questions. They help me because they keep me on track, and I think they help other students because if something's unclear, then it's not unclear just to you, it's unclear to other people, and maybe we can straighten some of those points out. So any questions up to now? Well, if not, let's get onto the board and we'll begin talking about water. Again, water is this unusual molecule. It has a molecular weight of 18. it's composed of 2 atoms of hydrogen and 1 atom of oxygen, and those atoms are linked one to another by something known as a covalent bond. The electrons are being equally shared by the oxygen and the hydrogen. Now, in fact, that's a bit of a misstatement. The qualities of water largely arise from the fact that the electrons within the water molecule are unequally shared, and that gives rise to something known as a dipole moment. And we're going to spend a lot of time today talking about that dipole moment and the consequent effects it has on the characteristics of water. But let's start here with just the simple idea that water is H2O. We all know that. And it tells us that there are 2 atoms of hydrogen and 2 atoms, what am I talking about? And 1 atom of oxygen. That, of course, is H2O. But if we look at it more carefully, what we see is that we have this oxygen atom with an atomic weight of 16. And then attached to that, by covalent bonds, which we show by these lines, we have 2 atoms of hydrogen. Now, remind you that what a hydrogen atom is simply a proton with an electron spinning around it. So it's the simplest of all of the atoms in the universe. And what happens with water is there's a kind of sharing of the electrons between the hydrogen and the oxygen. So this single electron out here of the hydrogen with its covalent bond is being shared with the oxygen. One of the unique characteristics here is that oxygen, because the atom is so much larger, is now borrowing the electrons. So if we look at the electrons spinning around in this molecule, Heisenberg tells us we don't know exactly where those electrons are. We don't know what their momentum is. But what we do know is that the electrons are being unequally shared, and that these electrons are spending more time around the oxygen atom than they are around the hydrogen. What this means then is that these electrons, because they're being sucked off and borrowed by the oxygen, gives a net negative charge here to the oxygen atom. Then out here, because the electrons are spending more time with the oxygen than the hydrogen, this gives this end of the molecule a slight positive charge. Would you note that this is not a G, that's a delta. That's meant to be a small delta. It's a Greek letter. It's telling us that this end of the molecule is slightly more positively charged, and this end of the molecule is slightly more negatively charged. Well, this is going to confer a number of interesting characteristics to this molecule. But let's take a minute to sort of emphasize and compare this molecule. Water has a boiling point at sea level of 100 degrees centigrade. It's a little less at our altitude. It has a freezing point of 0 degrees centigrade. So it's liquid between 0 and 100 degrees centigrade. Now, if we look at a similar molecule, like nitrogen and oxygen, and again, we're going to see later on in the course that nitrogen composes about 79% of the atmosphere, and water composes about 21% of the atmosphere. And we, of course, know that these are gases at room temperature. But if we look at these, nitrogen has a molecular weight of 28, 14 from each nitrogen. Oxygen has a molecular weight of 32. Both of these are bigger molecules than water at 18. So if we look at water, it's the molecular weight. It's 18. And yet, these have very different characteristics. If we look at the boiling point for nitrogen, it's minus 196 degrees centigrade. If we look at the boiling point for oxygen, it's about minus 180 degrees centigrade. That's an enormous difference. I mean, why is it that nitrogen doesn't boil until minus 196 degrees centigrade and water boils at plus 100 degrees? Almost a 300 degree difference. The answer to that question resides in this characteristic over here, this characteristic of the dipole moment. The dipole moment where charge on water is unequally distributed. And the reason for that is that those molecules of water can now interact with one another through the charges. Because oxygen and nitrogen are not charged in that way, they can't interact with the neighboring molecules, but water can. So let's redraw this, showing the oxygen and the two hydrogens. Now let's imagine another molecule of water out here. There's the oxygen and its two hydrogens. Put another hydrogen up here, hydrogen with the oxygen. Now, these charges, the charges on the hydrogen being slightly positive and the charges on the oxygen being slightly negative, those act like tiny magnets. And because of the magnetic nature of these ends of the molecule, the magnetic nature of the dipole, these negative ends on the oxygen can interact with the positive end of the hydrogen on the neighboring water molecule. Now, these interactions, these magnetic interactions, are called hydrogen bonds. And in liquid water, they're really, really short-lived. They only last a few picoseconds or so before the water molecule will then switch its orientation and find another water molecule to be attracted to. But the molecules in this solution of water, in this water construct, can interact with one another. And because they're interacting with one another, they're being held together by the hydrogen bonds. So hydrogen bonds keep water liquid. And the way we get water to boil is we simply put more energy into the water. So when you made coffee this morning and you boiled water, what you did is you heated water. And by heating the water warmer and warmer and warmer, you increase the thermal agitation on these water molecules. Until such a point, there was such agitation in here that those water molecules were no longer being held together by their hydrogen bonds. And they could then escape from the surface as water vapor, steam. But that also brings us to another concept. And that concept is the concept of surface tension. We're all familiar with this. And the example I'll give you is if I take a beaker of water and imagine the water molecules in that beaker of water. Remember that all of these guys, they're not going to be conveniently arranged like this. They're going to be randomly distributed, but let me just draw them this way. These water molecules are spinning round and round, and what they're doing is they're interacting with one another through those hydrogen bonds. And right at this air-water interface, the hydrogen bonding between the water molecules generates something known as surface tension. And a good example of surface tension is if you go out to a pond someplace in the summer and you look at the insects, you'll often see these insects on the surface of the water. And sometimes they're called Jesus bugs because they're walking on the water. And the way they do that is they have these very fine hair-like structures at the end of their legs, setae. And those animals are actually standing on the surface tension. They're standing on the surface tension because the interaction of these molecules of water through their dipole moments, through those electromagnetic fields, are so strong that you can actually take these small insects and put them on the water. Now you can do a trick. I don't suggest you do it, it's a little cruel, but if you take some detergent, and put it in the water, and what will happen is detergent molecules will now begin getting in between the water molecules, and they'll separate the water molecules from one another, increasing the distance of the hydrogen bonds. And if you increase the distance of the hydrogen bonds, then that weakens the interaction between the water molecules. You take that poor Weiderstrater and put it on the surface of the water with detergent, it'll sink like a stone because it can't stand the surface tension because of the detergent, you no longer have these water molecules being held together one to the next by those hydrogen bonds. So any questions up to there? Well, if not, let's spend a few minutes talking about concepts of hydrophilic and ion solubility and tie them back together into this discussion of the dipole moment on water. It's this unequal distribution of charge on the water molecule, which allows for other charged atoms, called ions, to go into solution. It's the charge-charge interaction which allows things like sodium and chloride to go into solution in water. Now, we're all familiar with this. We've all done the experiment at the dinner table where we've taken the salt shaker and shaken a little bit of salt into the water glass. And we know that that salt will easily go into solution in the water. But let's talk about that in a more formalized way, where we can imagine a beaker of water. And the bottom of that beaker, we're going to put, I'll just put it as a block. This is going to be sodium chloride. Sodium chloride contains an atom of chloride, a chloride ion, and an atom of sodium. In this sodium chloride crystal, for every atom of sodium, there is an atom of chloride, and they're all packed into a particular cubic structure. They're all stacked in one next to the other. But even in the sodium chloride crystal, these sodium ions and chloride ions are charged. The sodium ion has a plus charge, and the chloride ion has a negative charge. And now we have introduced the sodium chloride into water. And so Here are hydrogens. The covalent bonds between the hydrogen and the oxygen. And the dipole moments on the water molecule. And of course, we have trillions and trillions and trillions of these, and I'm just drawing a few of them. With its partial negative charge and partial positive charge. It's a bit of an exaggeration, but you can imagine these water molecules bouncing around in the column of water. And they're bouncing around with thermal energy. And they're bouncing around and they're striking the sodium chloride crystal. As they strike the sodium chloride crystal, these sodium ions now can be released from their crystal organization and go into solution in the water. So we can imagine this sodium chloride coming off as a sodium ion. I did it the other way. Coming off as a green chloride ion. And an orange sodium ion. Now, it's no surprise that these opposite charges are going to attract one another. So the positive charge in the sodium will be attracted to the negative end of the water molecule. And so I'll draw it out over here so that you have this sodium ion with its strong positive charge. And then the water molecules are going to orient in such a way that these oxygens, because they're of their partial negative charge, the dipole moment on the water, the negative charge in the oxygen is going to interact with this highly positive charged sodium. And so these water molecules are now all going to be surrounding this sodium ion. And in fact, there's something that develops here called a shell of hydration. Each of these charged sodium ions will have a shell of water molecules around it. And it will be true as well for the chloride. The chloride, which is negatively charged, will now have pointing toward it the hydrogens, which have their dipole moment of the positive charge, because the electrons have been stolen from them and all that's left is the positron. They will now have their negative, turn around. They'll have their positive ends of the hydrogen pointing toward the chloride. And again, there will be the shell of hydration that surrounds the chloride atom. It's just that the orientation of the water molecules will be different. The negative ends will be pointed toward the positive charged sodium, and the positive ends will be pointed toward the negatively charged chloride. But we'll now have this shell of hydration around the ions, and because of that, these ions go into solution in water. These ions are said to be hydrophilic. This comes from the Greek, it means water loving. So these water-loving molecules easily go into solution in water. Let's take a break, and we'll come back and we'll put some numbers on this, and we can talk a little bit about how these ions are going, these sodium chloride molecules will in fact completely dissociate into sodium ions and chloride ions. But let's take a 5-minute break, and we'll come back in a little bit and we'll finish the story. we've been, and then we'll begin to quantify some of that material. See if we can get the slides rolling here. Oh yes, I didn't have to have a pointer in the other room, and now I do, and I forgot it. Okay, so this is basically water. H2O is on the right-hand side, 1 atom of oxygen, 2 atoms of hydrogen, and this is a space-filling model trying to give you some scale sense of the difference in the size of the oxygen and the hydrogen atoms. The oxygen with a molecular weight of 16 is considerably larger than the hydrogen with a molecular weight of 1. And so what we see then is that because of the mass of the nucleus of that oxygen atom, that the oxygen is stealing the electrons. Because it's stealing the electrons, even though we have the covalent bond where the electrons are being shared between the hydrogen and the oxygen, they're not equally shared. That the electrons are spending more time around the oxygen than they are around the hydrogen, and that gives this differential charge, what we call the dipole moment of the water molecule. And so we have these charged ends of the molecule. Then this is showing the idea of hydrogen bonding. This is showing how the positive charge down here on the hydrogen ends of the water molecule are now being attracted to the negative end of the oxygen molecule. And these hydrogen bonds now are basically electromagnetic fields holding these molecules together. And they're bouncing around, bouncing one off the next with thermal energy. And if we heat it up high enough, then we'll vaporize these molecules and they'll be converted to a gas. And then the next figure is a crystal of sodium chloride. And you'll notice that for each one of those green negatively charged chlorides, there is a purple positively charged sodium. And those are interacting one with another in that cubic crystal. But if we put that cubic crystal into water, that we can now begin to put those individual ions into solution, and they'll form, with the water, they'll form a shell of hydration. So again, showing here, here's a positively charged sodium with the negative ends of the water molecule interacting with that sodium. There's a negatively charged chloride with the positive ends of the water interacting with that chloride molecule. That's what's allowing us to move from the sodium chloride crystal to putting those ions into solution. And that's the reason that they are hydrophilic. Yes?
So there's no bonding taking place with that, with the solution? It's just kind of suspended there with the charge? Or is it bonded?
They're not, those electrons are not being shared, but there's a charge-charge interaction. So that just as with the dipole moments on the water, these negative ends of the water will be interacting with the charge. It's just an electromagnetic field, they're being held in that way. But there's enough movement here that these things are moving back and forth. Now, to maybe answer your question, if we would take that solution of sodium chloride and we'd freeze it, then if we do it right, we'll separate the water from the sodium chloride. That's why icebergs are fresh water, because when they freeze from salt water, they separate out the sodium. The sodium doesn't freeze with it. For the most part, we don't trap the sodium and chloride inside that crystal. And in fact, when the water freezes, what's going on is we get the dipole moments of the water forming up into a crystal formation. That we lower the energy of those water molecules moving back and forth to the point where the water molecules are interacting one with another, and that forms then the crystal of ice. It's another unique characteristic of water, because when it forms a crystal of ice, it decreases its density. Most molecules, when they freeze, increase their density because the molecules become more closely packed together. But because of the peculiar arrangement of the dipole moments, the spaces between individual water molecules are slightly bigger in the frozen state than in the liquid state. And because of those larger distances of the hydrogen bonds in the crystal state, then we get the expansion of water. We know water expands when it freezes. If you've ever had pipes in your house freeze, you know they're going to break. And that's because of the expansion of the water. In the biological world, the reason that's important is that frozen water in the oceans will float. It doesn't sink to the bottom. If it sank to the bottom, we'd be living on a ball of ice. But because it floats, then we have the seawater stays below as salt water, and the freshwater ice comes to the surface. I don't know if that answers your question, but it fits with the kind of question you were asking. And what's my next one? Well, let's stop there and put things into solution. Well, let's come back to this figure. And let's think about what's going on in this figure and put some numbers to it. And I'm going to give you some numbers. Never remember these numbers. But the number I'm going to put on the sodium chloride here is I'm going to say that this is 5.84 grams. The reason I've chosen 5.84 is the molecular weight of sodium chloride is 58.4 grams per liter. And then we're going to imagine that this solution here is exactly 1 liter. So we have a 1 liter solution of sodium chloride. Now, because there are 58.4 grams per mole of sodium chloride, it means every mole of sodium chloride will contain 58.4 grams. All I've done here is I've taken a tenth of that and made this 5.484 grams, put that into solution. And then when all this goes into solution, this is going to make a 0.1 molar sodium chloride solution. Another way of saying 0.1 molar is to say that it's 100 millimolar. And in biology, we use this term millimolar a lot, millimolar and micromolar, because these are the kinds of concentrations of ions and molecules that we'll see in biological systems. So we're saying here that this is a 0.1 molar or 100 millimolar sodium chloride solution. But we need to drill down into this a little bit farther, because one of the characteristics here is that the sodium and the chloride will completely dissociate from one another, that they will become independent of one another when they go into solution. So even though we start out with 100 millimoles of sodium chloride, what we're going to find, because of the complete dissociation, is we're going to end up with 100 millimoles of sodium ion. And at the same time, we're going to end up with 100 millimoles of chloride ion. So although we started out with 100 millimolar sodium chloride, because of the characteristics of the sodium chloride being able to completely go into solution in water, completely dissociate into sodium ions and chloride ions, we now have 100 millimoles of sodium ion and 100 millimoles of chloride ion. This is a complete dissociation. But the next thing to think about is the idea of equilibrium. Let me come over here and open up a bit of the board here, and we can talk a little bit about what we mean by an equilibrium, coming to an equilibrium. And the major concept you need to hold on to whenever you're thinking about coming to an equilibrium is to remember that to reach an equilibrium, molecules or ions move randomly from a region of higher to lower concentration. Things go from where they are to where they're not. And you can imagine this of the sodium chloride crystal. You can imagine when we first put that sodium chloride crystal into the water, that as the water's buffeting the sodium chloride crystal, that the concentration of sodium ions and chloride ions will be quite high around that sodium chloride crystal, because it's basically being chipped off from the sodium chloride crystal. But over time, because of the thermal agitation and the random movement of these ions, the sodium and the chloride ions, in the water solution, just bouncing about randomly, because they're bouncing about randomly, given time, these sodium ions and chloride ions will be evenly distributed in the water column. Because they're being bounced about in a random fashion, it doesn't take very long, it takes some time, but these sodium ions and chloride ions now will be randomly distributed in the water column. So wherever you take a sample of the water out of the beaker, you'll have the same concentration of sodium ions and the same concentration of chloride ions, because they've come to equilibrium because of the random walk of those sodium ions and chloride ions from their point source down here of the sodium chloride out into the aqueous environment. Again, all of that's possible because the sodium and chloride completely dissociates into sodium ions and chloride ions. But we can take this idea of the random walk and change the story just a little bit. And we'll start with the same idea, where we're going to have a liter of sodium chloride, a liter of 0.1 molar sodium chloride, which is 0.1 moles of sodium ions, 0.1 moles of chloride ions. We're going to put that into one container, and then we're going to separate the container into two parts. So let's draw that. So we can imagine having this beaker like we had before, but now we're going to divide this beaker into two equal parts. Whereas over here, on the right-hand side, we're going to have only water. And on the left-hand side, we're going to have 100 millimolar sodium chloride, which of course means we have 100 millimoles of chloride and 100 millimoles of sodium ion. You can now think about these sodium ions and chloride ions as being ping pong balls, and they're bouncing around by thermal agitation in this chamber. As long as this is an impervious barrier, as long as nothing can get through the barrier, nothing's going to change. On the right-hand side, we're going to have water, and on the left-hand side, we're going to have 100 millimolar sodium chloride concentration. But now let's think about what happens if we start putting holes in that barrier. And in this particular case, to make it more biological, we're going to imagine that these holes are either sodium selective or chloride selective. And so we can put a channel across here. So we'll now say this is a sodium selective channel. And we'll put a green one in here, which is a chloride selective channel. Now in reality, if we were to do this experiment, we'd put thousands and thousands of these channels in. But all I wanted you to imagine here is that if we have the barrier and suddenly we have some of these sodium selective holes and then some of these chloride selective holes, that now and again, when these ping pong balls, the sodium ions, the chloride ions, bounce against this barrier, they'll hit it just right. And when they hit it just right, the sodium ion will move from the left-hand compartment through the channel to the right-hand compartment. And the chloride ion will move from the left-hand compartment to the right-hand compartment. Now again, things move from the region of higher concentration to lower concentration. And you can think about this for a moment and say, well, there are just trillions and trillions of these sodium and chloride ions on this side, none on this side. So the probability is clearly that it's going to move left to right. It's going to run down its concentration gradient. And over time, what's going to happen is by this random walk, we're going to go from 100 millimolar on this side. Let me do it this way. 100 millimoles of sodium on this side, and because they're moving, as the sodium is moving from the left compartment to the right compartment, simultaneously with the chloride moving from the left compartment to the right compartment, that given enough time, we'll now change the sodium concentration to 50 millimoles and the chloride concentration to 50 millimoles. But now if we look over here on the right-hand side, we've come to equilibrium, and we again now have 50 millimoles of chloride ion, and we have 50 millimoles of sodium ion. We've come to equilibrium. At that point, once we've reached equilibrium, then the probability of a sodium ion moving left to right is exactly the same as the probability of moving right to left. But until we reach that equilibrium point, because we have a difference in concentration, then we're more likely to move from left to right. But once we've reached equilibrium, concentrations are the same, the probabilities are now equal, moving in either direction. Yes, you had a question.
So in this scenario, would it still move even though there's water on that side, or would the water also move to the other side?
Okay, so your question is about the movement of water. And that's a really good question. And we're going to come to that in a moment. But now the caveat here is I've said in this barrier that there are no pathways for water. So there's no mechanism whereby we can move water from one chamber to the other. In the rules here are that we only have holes that are permeable to the ions. So we can only move the ions, we can't move the water.
Okay, so it would, even if there was a ton of water on the other side, it would still move to equilibrium?
It would still move to equilibrium, regardless of this amount of water. Because as long as we have only sodium ions and chloride ions, then they're going to reach equilibrium between sodium and chloride.
Okay.
All right. Now I'm going to, having said that now, I'm going to change gears to you and we're going to now move water.
Okay.
So are there any other questions then? So let's take the same story. Let's rewrite the story over here. So there's the beaker. There's the barrier. This is again 1 liter, but it's only water. And the left-hand side is again a volume of 1 liter, but it's at the same time 100 millimolar sodium chloride. So again, we have 100 millimoles of sodium ion and 100 millimoles of chloride ion. Right. Now, where in this story we had ion selective channels, what we're going to do now is across this barrier, we're going to put water selective. channels. And these water selective channels have a name in biology. They're called aquaporins. They're just a water selective pathway. Now, in our story here, ions can't move. They're stuck. There are no ion channels. But water can move. Now, think about this for a moment. We only have water on this side, but the volumes are the same in the two chambers. The volumes are the same in the two chambers, but some of the volume, some of the space is occupied in this chamber by sodium ions and chloride ions. So then the question is, in which of these two chambers is the water concentration higher? Is it higher where there's only water, or where some of the space of this volume is being occupied by sodium chloride? Well, there's simply more water on this side than this side. We simply have more water molecules in the pure water than we have in this compartment, where we have some of the volume occupied by sodium and chloride ions. That tells us that the water concentration, and the convention is to put this in brackets, the water concentration is higher on the right side. So the water concentration is greater here than here. Things go from where they are higher concentration to lower concentration. So what we're going to see is the water is now going to move down its concentration gradient through these selective pathways, the water selective pathways, through the aquaporins. So water is now moving from its region of higher concentration to lower concentration. And this process of water moving from higher to lower concentration, and the lower concentration of water in this compartment being derived from the fact that some of the volume is taken up by the ions. This process is said to be osmosis. Osmosis is the movement of water down its concentration gradient. Now there's an aside here, and it's not going to be important to us here in biology, but there's a case where it is important. And I want you to think about this, because there's a kind of logical conclusion to this that's important. And that is, because the ions are confined to this chamber, water can move from the region of higher to lower concentration, but the ion concentration on this side is always, always, always going to be higher than on this side. You can never get to zero ion concentration on this side by simply moving water. So what happens is water keeps moving and moving and moving. But then the question arises, how do we get to an equilibrium? And this is something we'll run into a little bit later when we talk about the concept of hydrostatic forces. So the water is moving from the right chamber to the left chamber. The water volume in here is getting higher and higher and higher. So the mass of water is getting greater and greater. So the way we reach equilibrium here is where the osmotic force moving water right to left is balanced by the hydrostatic force of the water in the column. Apparently, this is basically the way the plants work. So that if you go out and look at some of the trees outside, what the trees are doing is we put water into the soil. Some places it rains, but here we put water into the soil, and the water now moves into the cells of the tree, into the roots. And there's a salt differentiation. There's a salt concentration inside the cells. So water's moving into the cells. And it's moving up through the plant by this osmosis. But there's a point at which the water column gets to be so massive that we reach an equilibrium that we can't draw any more water. That limit, I think, is less than 100 feet. And then you say to me, well, but there are places where we have trees that are taller than 100 feet. Go to the West Coast and you'll see the redwoods. But the redwoods always live in a particular environment. They're always found in a coastal environment where there are steady onshore breezes where water is in the air. And these coniferous trees, the redwoods, will actually take water out of the air. And that's one of the reasons they're not restricted by this typical movement of water up through their water vascular system, because they can actually take water directly in through their coniferous leaves. That's an aside, it has nothing to do with this course. But I just think it's an interesting idea, and it's an upshot of this idea that we have ions here, we have pure water out here, we never can reach equilibrium, so there's always a draw, there's always a diffusion of water from region of higher to lower concentration. Any questions to there? If no questions, let's move on and move from this idea of hydrophilic to the concept of hydrophobic. Hydrophobic is pretty much the other side of the coin from hydrophilic. And I'm going to tell the story here from the point of view of two great extremes. We've been discussing the hydrophilic nature of those highly charged particles, the ions, sodium and chloride. Could be calcium ions, it could be sulfate ions. They're highly charged, so they're hydrophilic. Whereas now what we're going to do is we're going to talk about molecules where the electrons are equally shared. The case of the sodium ion is that the sodium ion has an extra positron in its nucleus, so it has an extra charge. With chloride, the chloride has an extra electron in its valence shells, so it's negatively charged. So they're really highly charged particles. We're going to move now to molecules that are largely uncharged, and we'll see how the uncharged nature of these molecules gives rise to peculiar characteristics in their interaction in water, and therefore peculiar characteristics in biology. So we'll take this panel and we'll describe the concept of lipids, specifically triglycerides, as hydrophobic molecules. Now, to do this, we have to spend a little time with some chemistry. And we're going to see that these triglycerides are based on one molecule of glycerol and three molecules of fatty acid. Now let's look at some chemistry. Now biology will not make these molecules in the same way I'm going to show you here. Biology makes them making fatty acids 2 carbons at a time, but that's a detail. What I want to show you here is we start out with a 3-carbon alcohol. This is glycerol. It's a 3-carbon alcohol because it has these 3 hydroxyls. There are 3 carbons, each of the carbons is connected covalently to a hydroxyl. That makes it an alcohol. You remember from chemistry that carbons always have to have 4 bonds. So here are your 4 bonds. So that's the 3-carbon alcohol of glycerol. And the next characteristic we're going to put in here is we're going to put in a molecule out here and just line it up so that we now have a carbon, double bonded oxygen, and an OH. And then we have this great long string of carbons. I won't draw them out. But in biology, typically, we have 16, 18, 20, or as many as 22 carbons in a fatty acid. It's said to be an acid because of this group up here, the C double bonded oxygen OH. This is said to be a carboxylic. Doesn't look right. Acid group. Now, these carbons will have, in many cases, will have hydrogen surrounding them. If all of the carbons have hydrogens, this is said to be a saturated fatty acid. But in some cases, we have the same arrangement with a C double bonded oxygen, OH, carboxylic acid. And then we have this long string of carbons. And now and again, there'll be a double bond. Now, in order to make sure we have 4 links on each one of these, then this will be 1, 2, 3. There's only be 1 hydrogen here and 1 hydrogen here, and then the rest will be. So this is said to be unsaturated. Some of these fatty acids are monounsaturated. That means they only have 1 of these double bonds in them. Some of them are polyunsaturated. There are a few of them have triple bonds. That's not important. What's important, though, is that whenever we look at these molecules, whether they're arranged in this fashion or whether they're saturated, that if you look at the electrons, all of the electrons are being equally shared. There's no place on here, except maybe a little bit out here for the double bonded oxygen, where the electrons aren't equally shared. Because they're all equally shared, these long strings of carbons and hydrogens are uncharged. We can put another one down here. Put this one in, well, as well. As an aside, you notice what I did here? I put the hydrogens on opposite sides. That's said to be a trans fat. And if you've read about trans fats, the trans fats are, biology can't deal with these. We don't know how to digest them. And that was a real boon, because you could use fats and put them in baked goods and put them on the shelves, and because no biological entity could digest them, they'd remain fresh for weeks, months. The problem is we can't deal with them either. And so these trans fats become a problem, and we think that this is one of the causes of plaque building up in arteries because of these trans fats. And it's because of this peculiar arrangement of the hydrogens. And we made these through our wonders of chemistry, put them into foods, and it's now said that there is no safe level of trans fats. So they're trying to eliminate them from all of our diet. And that's simply, this is a trans fat. Up here, the one I showed was a cis. It's on the same side. But now, so far, all we've done is we've shown the 3-carbon alcohol, and we have shown the carboxylic acid. Now what we're going to do is we're going to do something known as a dehydration synthesis. And in a dehydration synthesis, what we're going to do is we're going to generate water and create a covalent bond. The chemical reaction here is to take the hydrogen from the alcohol on the 3-carbon glycerol and generate out here a hydrogen and an OH. It's a water molecule. And now what we can do is, because of that dehydration synthesis, we can form a new bond. We can form a bond now that goes from the carbon to the oxygen to the carbonyl carbon here. So it's a carbon, oxygen, carbon, double bonded oxygen. Now, many of you haven't had any organic chemistry yet, but you'll learn in organic chemistry that when you have such a bond that goes from carbon, oxygen, carbon, double bonded oxygen, that particular bond has a name. It's called an ester bond. We can do this, or we can repeat this pattern for all 3 of these fatty acids. So we can now go to this number 2 one, again do the same story. Do a dehydration synthesis. We get a hydrogen hydroxide. And we form this ester bond. Now I want you to hold on to this idea of the ester bond, because the ester bond is really an important bond here in thinking about the triglyceride. And we can do this in all 3 cases. So now we're going to have 3 ester bonds linking the 3 carbons of the glycerol to the carbonyl carbon of the carboxylic acid. In this way, now we can take 3 molecules of fatty acid, covalently link them through the oxygen that had been the alcohol of the glycerol, and form these covalent bonds, and this structure now is a triglyceride. It's a triglyceride made from a molecule of glycerol and 3 molecules of fatty acid. One of the points I want you to see here is that all of these electrons are equally shared. And we know this. We know this from everyday life. We know, for example, that if you go home today and have lunch, and I'll go back to the upper panel, and you decide you're going to have a salad for lunch, and that you're going to make yourself a salad dressing. And when you make the salad dressing, you're going to basically take a carafe, and you're going to put the olive oil, or some other kind of oil. It could be corn oil or safflower oil or any number of vegetable oils, but typically for a salad dressing, we'll use olive oil. And you take this carafe, and you put in some olive oil. L. And then to that, you'll add usually vinegar. Well, vinegar is mostly water. It's just an acetic acid solution, so it's mostly water. So basically, you're adding water to this thing. And you know that if you put water on top of the olive oil and let it sit, it won't be very long until the olive oil will separate out from the water. You'll basically get a layer of olive oil on the top and the water vinegar solution down here. If you try to do the same thing with sodium chloride, to go into solution. But when you do this with a triglyceride, because the triglyceride is hydrophobic, it doesn't go into solution. And the reason it doesn't go into solution is that there are no open charge sites to interact with the dipole moments in water. All you have is that double bonded oxygen. It's just not enough to allow these hydrophobic molecules of triglyceride to go into solution. So they separate out. Well, you know that you could take this carafe and you could shake it. You could shake it and shake it and shake it. And after a little bit of time, you'll get this carafe. And you'll get the water. And you'll get little bubbles of olive oil. But it won't be very long before all those olive oil bubbles coalesce and you get back to the separation because they simply aren't soluble in water. They're hydrophobic. In the last few minutes, let me introduce one more idea. I'll do that in the backboard. And where we have emphasized up here a molecule which is extremely hydrophobic, what I want to do in the backboard here is I want to emphasize the idea of something called amphipathic. Again, it comes out of the Greek meaning both, feeling. And these are molecules that can interact with water and hydrophobic regions. The molecule of the amphipathic molecule we're going to concentrate on here is one known as a phospholipid. Let me draw one of these out for you in the last minute or so. And what we'll see is it too is based on the 3-carbon alcohol of glycerol. It too obeys all of the rules of organic chemistry. So that there's going to be this oxygen to a carbon to a double bonded oxygen, that's the ester bond, plus this great long chain of carbons. I won't bother to put all the hydrogen in. And another one here. So this molecule looks like the molecule we have in the upper panel, but now we're going to change things down here at the number 3 carbon. At the number 3 carbon, we're now going to take the hydroxyl again. So here's the oxygen. But we're going to link that oxygen now to a phosphorus, to an oxygen. And this phosphorus will have a double bonded oxygen and an O negative. And then this oxygen out here is now going to be linked covalently to one of 3 molecules. Could be serine, it could be ethanolamine, it could be choline. What all 3 of these have in common is they're charged. We'll see later that serine's negatively charged, the other 2 are positively charged, but this is said to be a charged phosphate head group. The charged phosphate head group is basically hydrophilic, where these fatty acid side chains are hydrophobic. And since we're running out of time, what we'll do tomorrow is we'll think about how these molecules, which will abbreviate as a circle with the head group and the squiggles with fatty acid side chains, how are these molecules going to interact with water? We'll start with that tomorrow, and we'll start making bilayers out of them. And then from that, we'll generate the lipid mosaic model of the membrane. So if there are no questions, I can let you go. Okay.